Welcome to this presentation covering the air conditioning system on A320 series aircraft. Like the majority of the aircraft systems, the air conditioning system is fully automated and requires minimal attention. Two computers carry out the air conditioning system automation. These computers are referred to as air conditioning system controllers. They receive inputs from aircraft sensors and cockpit and cabin controls to maintain the desired temperature throughout the aircraft. Then they issue instructions to various valves and their respective pack. Each controller has two independent channels to provide redundancy. They are referred to as lanes. One lane is active, the other lane is available as a backup. A320 series aircraft are equipped with two air conditioning packs located in the belly, just forward of the main landing gear bay. Each air conditioning system controller is responsible for its associated pack. We will primarily cover only those elements of the packs that you can control or monitor. We will start with the pack flow control valves. Hot bleed air from the pneumatic system enters each pack via these valves. These valves adjust the rate of airflow through the packs. These valves are normally controlled by the respective air conditioning system controller, but can also be controlled by the crew. After the bleed air passes through the pack flow control valve, it enters the primary heat exchanger. The heat exchanger uses ambient air to cool the bleed air. The air conditioning system controllers control the pack outlet temperature by modulating the pack air inlets on the belly of the aircraft. This adjusts the amount of ambient air flowing through the pack heat exchangers. The ambient air is expelled through the outlet located further aft on the belly of the aircraft. The crew can neither monitor nor directly control the inlets or outlets from the cockpit. To avoid ingestion of foreign objects, the inlets and outlets automatically close during takeoff and landing. The cooled bleed air then enters a compressor, where it is compressed and the temperature increases. The air is cooled again in the main heat exchanger and enters the turbine section, where it is allowed to expand, cooling the air even further. The energy extracted by the expansion is transmitted by a shaft to spin the compressor. The removal of heat during this process reduces the temperature of the air, resulting in a very low pack outlet temperature. A ground cooling fan mounted on the turbine shaft ensures airflow through the heat exchangers when ram airflow is not sufficient, for example, ground operations. It is not depicted here, and this is the last time it will be mentioned. The compressor and turbine are sometimes referred to collectively as the air cycle machine, or ACM. A key tool used by each controller to control the output temperature of each pack is the bypass valve. The more warm air that this valve allows to flow around the air cycle machine, the warmer the pack outlet temperature will be. The bleed page can be used to monitor the operation of key components of the pack. The position of the pack flow control valve and the flow rate are depicted. Even though the valve modulates as necessary to provide the appropriate flow, the valve is either depicted as open, closed, or in transit. Because it is the area most prone to overheat, the pack compressor outlet temperature is also displayed. pack bypass valve position is displayed. This valve is commonly misunderstood. Basically, if it is cold outside and a warm cabin is selected, the valve moves to the open position to allow some of the warm bleed air to pass some of the cooling cycle. If it is hot outside and a cool cabin is selected, the valve moves to the closed position to allow the maximum amount of air to be cooled by the pack.
And finally, the pack outlet temperature is also displayed on the bleed page. This is the temperature of the air as it exits the pack.
Now that you are familiar with basic pack operation, we will discuss how the air is used. Conditioned air from the packs is provided to a mixing unit. The mixing unit in turn feeds three separate aircraft zones: the cockpit, the forward cabin, and the aft cabin. The air conditioning system controllers monitor the temperatures in the three zones and use this information to control the outlet temperature of the packs. The controllers determine the coldest required zone temperature and command both packs to provide air that is that temperature. Because the packs produce the coldest air required, the controllers must use another tool to control the temperature in the three zones. Hot air is tapped directly from the pneumatic system and routed through a hot air pressure regulating valve. This hot air is then provided to three trim air valves that are also controlled by the air conditioning system controllers. The trim air valves open and close as necessary to warm the cold pack air to reach the desired temperature in each zone. The system also incorporates two cabin fans. They provide recirculation airflow from the cabin back to the mixing unit. This reduces the bleed air demand through the packs, resulting in fuel savings. An emergency ram air inlet is located on the belly of the aircraft. It can be used to direct external air directly into the mixing unit. It may be used for cabin ventilation if both packs fail, or to assist in clearing cabin smoke. Now that you are familiar with the basic design of the air conditioning system, we will move on to the controls and indicators. Air conditioning system indications are provided on 4 different ECAM pages. On the cruise page, the temperature in each of the 3 zones is displayed in degrees Fahrenheit. On the cabin pressure page, the packs are represented at the bottom of the page. They are normally shown in green and white. If a pack flow control valve is closed and the associated engine is running, the respective pack is displayed in amber. Now we move on to the bleed page, where there is much more to talk about. The lower half of this page is dedicated to the pneumatic system and is discussed in the pneumatics lesson. Indications for the packs, mixing unit, aircraft zones, and ram air inlet are displayed on the upper half. Let's take a closer look. Both packs are shown. We'll take a closer look at them. The pack flow control valve and pack bypass valve are displayed at the bottom of the pack. If the valve is normally closed, it is depicted cross-line green. If the valve is closed, but its position disagrees with the commanded position, it is depicted cross-line amber. If the valve is normally open, it is depicted inline green. If the valve is open, but its position disagrees with the commanded position, it is depicted inline amber. This valve is unique amongst air-related valves in that the ECAM also shows the amount that the pack flow control valve is open using the pack flow indicator. The pack flow indicator is depicted on the bleed page as you see here. The digital pack compressor outlet temperature readout is normally green. It changes to amber if the pack compressor outlet temperature is excessive. An ECAM message would also be displayed. You can monitor the operation of the bypass valve. This needle is always green. If the needle is more to the left, the valve is more closed, resulting in colder pack output. The more to the right, the more open the valve, allowing more hot air to bypass the air cycle machine, resulting in hotter pack output. Just remember C for cold and H for hot. The digital readout of the pack outlet temperature is normally green. It changes to amber if pack outlet temperature is excessive. The mixing unit and the 3 zones are depicted at the top of the bleed page. They are normally green. The mixing unit is displayed in amber if both pack flow control valves and the ram air inlet are closed. The ram air inlet is also depicted on the bleed page. The various possible ram air valve indications are displayed here. Even if the inlet is open and in agreement with switch position, it is displayed in amber. This highlights the fact that a deployed ram air inlet is not a normal aircraft configuration. The lower half of the condition page displays information relating to the cargo hold ventilation. It is discussed in the ventilation lesson. The upper half of the condition page displays the hot air pressure regulating valve, trim air valves, zone duct inlet temperatures, and zone temperatures. The hot air pressure regulating valve is labeled hot air. It can be displayed in the various ways you see here. The valve is displayed in amber when selected closed by the crew. Although it is in agreement with switch position, it remains amber to highlight the fact that this is an abnormal configuration. The trim air valves are depicted to the left of the hot air valve. Let's assume the crew has set the controls for 70 degrees in the cockpit and 72 degrees in the forward and aft cabin. The packs will provide 70-degree air because that is the coldest temperature requested. The trim air valves add hot air to increase the temperature as necessary. In this example, the forward and aft trim air valves are partially open to warm the respective zones to 72 degrees Fahrenheit. The condition page also displays the zone duct temperature. This is the temperature of the air as it enters the zone. The condition page also displays the actual temperature in each zone. Zone inlet duct temperatures are normally shown in green. They change to amber if the zone inlet duct temp exceeds a preset limit. The actual temperature in each zone is always displayed in green. Fan is displayed if the respective recirculation fan fails. We now move on to the overhead air condition panel. Most of the controls on the bottom of the panel are associated with pneumatic system and are discussed in the pneumatics lesson. The guarded ram air push button is used to open the ram air inlet. Advance to open the ram air inlet. The ram air valve will be discussed in more detail in the abnormal operations section. The Pack 1 and Pack 2 push buttons control the associated pack flow control valve. Advance to select Pack 1 off. Pack 1 is now off and the valve is indicated closed. The fault light in a pack push button illuminates if any of the following occur. Pack flow control valve position disagrees with the commanded position. A pack compressor overheat is detected. A pack outlet temperature overheat is detected. The valve closes automatically if an overheat is detected. In this example, a pack compressor overheat has been detected. The pack flow selector allows the crew to select a desired pack flow. 3 settings are available. Low equals 80% of normal flow, norm equals normal flow, and high equals 120% of normal flow. This information is provided to the air conditioning system controllers, not directly to the pack flow control valves. We will look at the use of this selector in more detail in the normal operations section. The 3 zone temperature selectors are used to adjust the desired temperature in the respective zone. For reference only, cold equals 64 degrees Fahrenheit, 12 o'clock equals 76 degrees Fahrenheit, and hot equals 86 degrees Fahrenheit. This information is provided to the air conditioning system controllers, not directly to the trim air valves. Individual cabin zone temperatures can be adjusted via the forward attendant panel, plus or minus 5 degrees Fahrenheit from the cockpit selected temperatures. The hot air pressure regulating valve may be closed using the hot air push button. Advance to see an example. The hot air pressure regulating valve is now closed. This causes all the trim air valves to also close, thus limiting the ability of the controllers to adjust the temperature in the zones. The hot air push button should only be used when directed by a specific procedure. The fault light in the hot air push button illuminates if a duct overheat is detected. If that occurs, the valve closes automatically, causing the trim air valves to also close. One of the ECAM steps would be to select the push button off. Advance to select hot air push button off.
With the push button selected off, the fault light extinguishes when the overheat condition no longer exists.
The last air conditioning control we will discuss is on the ventilation panel. The cabin fan's push button can be used to control the recirculation fans. The cabin fans run any time AC power is established. Advance to select the cabin fan's push button off. Both recirculation fans have stopped and are displayed in amber on the condition page. This completes the controls and indicators section. You have just arrived at the aircraft. The APU is running and powering the aircraft. The APU bleed air is not being used. During the pre-flight of the overhead panel, it is normal to see the fault lights in the pack push buttons illuminated. This is because the pack flow control valves are closed due to lack of airflow. That is currently the case since the engines are not running and the APU bleed is not being used. You should also see lights out on the ventilation panel during the pre-flight. Now let's provide some air to the packs. You would normally do this, but we will display the bleed page for academic purposes. Notice that both pack flow control valves are closed due to the lack of air. Advance to select the APU bleed push button on. The APU bleed valve opens and immediately supplies the left side of the system. Normally, after a brief delay, the cross bleed valve would open automatically to provide air to the right side of the system. We have stopped the process here to point out a few things. Pack 1 is now operating and the fault light in the Pack 1 push button has extinguished. The mixing unit changes from amber to green. Advance to observe the right side being supplied. The cross bleed valve is now open. Pack 2 is operating. Notice that both packs are providing high flow, even though the pack flow selector is in the norm position. The air conditioning system controllers automatically command high flow when only APU bleed air is being used or if operating on one pack, regardless of pack flow selector position. We will now display the condition page and discuss how the system controls the temperature in the zones. Current temperature throughout the aircraft is 65 degrees Fahrenheit. The requested temperature is 76 degrees Fahrenheit in all three zones, with the zone temperature selectors in the 12 o'clock position. The air conditioning system controllers react to this situation by opening the trim air valves to provide warmer air to the zones.
In this example, the cockpit has reached the desired temperature first and the trim air valve has partially closed to reduce the amount of hot air added to the pack flow. Trim air valve operation will continue in this manner to maintain the desired temperatures.
We now move on to starting the engines. Reminding you again, the bleed page would not normally be displayed. Advance to rotate the engine mode selector to the ignition start position. When the engine mode selector is rotated to ignition start, the pack flow control valves close. This ensures all APU bleed air is available for engine start. If an engine is not started within approximately 30 seconds, the pack flow control valves will reopen. They will close again when an engine master switch is selected on. Advance to start engine 2. Now let's start engine 1. When engine start is complete, the pack flow control valves open and the APU bleed air supplies the packs. Using APU bleed air during takeoff increases takeoff performance because engine bleed air is not being used to operate the packs. Normally, the APU is shut down shortly after engine start. advance to select APU bleed push button off and shut down the APU. The engine's bleed valves open automatically. The engines will provide bleed air to the packs for the remainder of the flight, assuming no malfunctions occur. Notice that pack flow is reduced now that the engines are providing air to the packs. On flights with lower passenger counts, the pack flow selector may be set to low. This reduces engine bleed demand and conserves fuel. With a high passenger count and high ambient temperature, it may be necessary to select high flow and cold zone temperatures. More fuel will be used. Return the selector to norm as soon as possible. Refer to your aircraft manuals for specific procedures. We have completed our flight and are about to leave the aircraft. To conserve fuel, the APU has been shut down. To maintain a comfortable cabin temperature in preparation for the next flight, the ground crew has connected an external air conditioning unit. It is now connected via a low-pressure connection point on the underside of the aircraft. Air is provided directly to the mixing unit and then into the 3 zones. There are no direct indications in the cockpit of whether or not external conditioned air is connected. This completes our normal operation section of this lesson. Now let's take a look at some air conditioning system abnormals. A Pack 1 overheat has been detected. We have canceled the master caution lights for you. The bleed page is displayed automatically. The pack compressor outlet temperature is displayed in amber. The Pack 1 flow control valve closed automatically. It is displayed in amber because its position disagrees with the switch position. Pack 2 goes to high flow with only one pack operating. The first ECAM step is to select pack push button 1 off. Advance to perform that step. Now the valve and switch positions agree, so the valve is displayed in green. The off light in the Pack 1 push button is now illuminated. The fault light remains illuminated as long as the overheat condition exists. The ECAM procedure includes a white condition statement informing you that you may attempt to operate the pack when the overheat subsides. The fault light has extinguished. The temperature indication on the bleed page is now displayed in green. Advance to select Pack 1 push button on. Pack 1 is now operating. The ECAM message is no longer displayed and the cruise page has replaced the bleed page. If the overheat returns, it may be necessary to discontinue operating the pack. Remember that the air conditioning system controllers are equipped with 2 channels referred to as lanes.
If one lane fails, it has no impact on system operation. The other lane can provide all necessary functions. Advance to fail lane 2 and watch what happens.
If both lanes of the same controller fail, the associated pack is lost and the hot air pressure regulating valve closes automatically. This results in the trim air valves also closing. Temperature regulation is degraded and is now performed by the remaining controller by adjusting the flow and outlet temperature of the remaining pack. That concludes the abnormal operations section. In this example, Pack 1 and Pack 2 have failed. The ECAM directs you to select the packs off. Advance to select Pack 1 and 2 push buttons off. If you haven't already, you should initiate a descent. Let's assume delta P is less than +1 psi. Advance to select ram air push button on. External air is now directed to the mixing unit for cabin ventilation. Selecting the ram air push button on sends a signal to the outflow valve and the ram air valve to open if delta P is less than +1 psi. If delta P is greater than +1 psi, neither valve will open. Note, the ram air valve will not open if the ditching push button is selected on. The outflow valve will not open if the mode select push button is selected to manual. Let's take a look at some of the air conditioning system differences. Some A321s have a zone controller that oversees the operation of the air conditioning system. Sensors and controls provide inputs to the zone controller, which sends signals back to pack controllers. The pack controllers then send signals to their respective pack. Newer aircraft have air conditioning system controllers. Aircraft with a zone controller do not have cabin temperature controls on the forward attendant panel. The zone controller has two channels, a primary and a secondary. The primary channel controls the air conditioning system. The secondary channel provides some control if the primary channel fails and also provides temperature indications on the condition page. The pack controllers also have two channels, a primary and a secondary. The primary channel controls its respective pack. The secondary channel provides some control if the primary channel fails and also provides indications on the bleed page. Instead of a pack flow selector, some A321s have an Econ flow push button. Selecting the push button on may reduce pack flow up to 20%. On all aircraft, the air conditioning system will command a higher flow than that is selected by the crew if it is necessary for a system operation. For example, in a single pack operation, the remaining pack will go to high flow regardless of switch position.